Okay, everyone, welcome to another past paper marathon session here. So today we'll be working through the June 2016 Cape Chemistry Unit 1 Paper 2. Okay, so let's go ahead and get started. So this is question 1 from Module 1, Fundamentals in Chemistry. So this question is asking us about John Dalton and his atomic theory. So it says we're supposed to say 3 postulates of Dalton's atomic theory. So 3 postulates of Dalton's atomic theory. The first one is that all atoms of the same element are exactly alike. His second postulate states that atoms cannot be broken down any further. He also postulated that atoms of different elements they have different masses. Okay, so just to recap, all atoms of the same element are exactly alike. Atoms cannot be broken down any further. That's the smallest indivisible unit according to Dalton. And he also stated that atoms of different elements have different masses. Okay, so those are 3 postulates of Dalton's atomic theory. So now we're going to keep moving down and let's just clear those. So then they're asking us, let's see, for 2 marks, that they're saying that later development in science led to the modification of Dalton's atomic theory, which we were just discussing above. Explain the modification of one of the postulates. Now, there are several modifications, but the one that we'll focus on here for these 2 marks is the first one, actually, where he said that atoms of the same element are exactly alike. We now know that that's not true, right? Because we now know that atoms of the same element, right, can have different masses. We know that, right? And properties as well, right? So we now know that atoms of the same element can have different masses and properties, contrary to what Dalton postulated, that they had to all have the same mass and same properties. We now know that that's not true. And so this is something that we see in isotopy, right? This is seen in isotopes. Because remember what an isotope is, right? Isotopes are atoms of the same element that have a different mass, right? So a classic example of an isotope would be chlorine, right? So we have 35 Cl, right? And we have 37 Cl. Now the atom, the element is chlorine, right? But we see that there are 2 atoms here that are both of chlorine, but they have different mass numbers. You see that? One is 35, one is 37. So that's a modification here that was made to one of these postulates, is that, atoms of the same element can have different masses and properties, and this is seen in isotopes. Okay? All right. So moving right along for part B, the dichromate 6 ion reacts in an acidic medium according to the following half equation, right? So we have our dichromate 6 ion reacting with 14 H plus ions plus 6 electrons to yield 2 moles of chromium 3 plus and 7 moles of water. So they're saying identify the ion that's responsible for the green color, right? And so what happens is that initially starting out, our chromate 6 ion is generally orange, right? So let's see, this one is generally orange. So the chromate 6 is orange. So let me just put that here. That this is the one that's usually orange. And then once that gets reduced, right, to Cr3+, that's when we see that green color. So then the ion responsible for the green color then is this one. Right, so we go from orange to green, and the green color is from the Cr3+. So let's just write that, the Cr3+ ion. Right, that's the one that's responsible for the green color, and that's for 1 mark. We're good. All right, so clear that. Moving right along. Given that the sulfate, right, so this is the sulfate 4 ion in SO3, 2-, is converted to the sulfate 6 ion in this SO4, 2-, when it's in the presence of water. So if the sulfate ion is in the sulfate 4 ion is in the presence of water, it gets converted to the sulfate 6 ion, right? So that's an oxidation that's taking place, right? Because we're going from, let's write that here, we're going from 4, right? And then we're going to 6. So that's an oxidation taking place. So when the sulfate 4 ion is in the presence of water, right, there's a conversion that goes from the +4 state to the +6 state. And so they're asking us to deduce the balance equation for the redox reaction between the chromate 6 that we were talking about earlier and the SO3 2- ion. Okay, so here's how we're going to go about that. So a redox reaction, so there are 2 halves to it, right? There's a half from which oxidation is coming from, and there's a half from which the reduction is coming from, right? So let's write, first we're gonna write out our reaction for our chromate that we already knew from up here. So let's just write that down as Cr207 2-. Right, and that's just gonna go to our 2 moles of the chromate 3+, that one that responsible for green color, as we mentioned above, right? Plus 7H2, right? So that's that half equation that they gave us in part I, right? Okay. So now what remains is we have to write the other half, and this was our what? So we're going from 6 in this case. We're going from 6, right, to 3. So this is a reduction. So I'm just gonna write that this one corresponds to the reduction of Cr6+, right, to Cr3+. Right, so let me just put this here. So we are going from, again, Cr6+ to Cr3+. So this is a reduction in a half equation. And then the other one that we're going to write is for the sulfate 4 ion, right, going to sulfate 6. So that's our oxidation half of this, right? So we're going to write SO3 2- aqueous plus water, because they told us that it was when it's in the presence of water, right, that we get this conversion now to the sulfate 6 ion, which is SO4 2- aqueous, right, plus what? So we get 2H plus and 2 E's, right? And this represents our oxidation of the sulfate. So I'm just gonna put S plus 4 to S plus 6. All right, because those are the changes in oxidation state that we see here. So here we end up at plus 6. And here the sulfur was plus 4. Right? Okay. So then what remains? Let me fill out my state symbols for this one and this one. So then what remains now, guys, is for us to add these two equations together, right? So we're going to add them together. But in order to add it, we have to make sure that the number of electrons are the same in both half equations. So we're going to have to, we see that there's 6 electrons up here. So we're going to have to multiply this bottom one by 3 to make sure that these electrons that are gained, right, by the dichromate 6 mirror what are lost by the sulfate 4. Okay, so we have to multiply this by 3 so that the amount of electrons that are gained in our reduction match the amount that are lost in our oxidation, right? So we have to multiply the bottom part by 3. And so what we'll end up with then is when we add them together, right, we're going to end up with Cr 2O7 2 minus aqueous, right? Plus 3SO3 2 minus, right? And then looking at let's look at this H here. So we have 14H plus up here, and down here we would have 6H plus when we multiply through. So that would leave me with what? That would leave me with 8 H pluses, right? So 14 and then minus the 6 that's over here. So that will leave me with 8 H pluses. So let me write that. Plus 8 H plus, right? And then of course the 6E is gonna cancel with the 6E that's on the other side down here. So my electrons go away. And then now what else? Or water, let's account for the water down here, right? So in the top reaction, we have 7 moles of water. And in the bottom reaction on the opposite side, we would have 3 moles of water, right? So when you subtract those two, 7 minus 3, you'll end up with 4, right? But the 4 is gonna end up being on this side. So we don't write it over here. So let's just continue on. So on that side, we'll have 8H plus aqueous. And then continuing on now, we're going to have our chromium, right? So that would be 2Cr3 plus. Plus now we can put our water, because here's our water, but we said it's 7 minus the 3 from over here. So that would get us what? 7 minus 3 would get us 4. So that's 4 moles of water, liquid, right? I put my aqueous on my chromium 3. And then now we are also gonna have, we took care of this already, right? So what remains then is this sulfate, 3 moles of SO4 2 minus, right? Plus 3 moles of SO4 2 minus aqueous. So that's our answer, right? So everything checks out there. We see that we're going from the chromium dichromate 6 to dichromate 3. And then here we're going from the sulfate 4, right, to the sulfate 6. So that's how that works. So this would be your answer for 4 marks, okay? So that's how you're expected to deduce that balanced equation. Okay? All right. So let's go down to the third part of this question, which is they're asking us to identify the oxidizing agent in B part 2. So let's bring back that and look at it, right? So when we look at this equation here, right, what we know about oxidizing agents is that oxidizing agents are the agents that bring about oxidation in other species, right? So the agent that brings about the oxidation in other species. So what was it that caused the sulfate 4 to be oxidized to sulfate 6? It was, in fact, the dichromate 6 ion that did that, right? Because by reacting with this dichromate 6 ion, this sulfate 4 went to sulfate 6, while the dichromate 6 itself was reduced in that process and went to the 2Cr3 plus, right? So oxidizing agents bring about oxidation in another species, right? While they themselves are reduced. And so the dichromate 6 ion is our oxidizing agent in this particular equation. So let's just scroll down, clear everything, and just write that down, that the oxidizing agent above was our dichromate, right? That was our dichromate 6 ion that brought about that oxidation. Okay? All right, so that's our answer for 1 mark here. So we're going to clear that and move on to part C. So part C is saying that the results of 2 tests are to be recorded in this table, table 1, and they're asking us to complete the table by inserting the missing observations or inferences, right? So here we go now. So they're saying that the test, right? So let's write out our tests. So they're saying that chlorine water, right? So that's Cl2 aqueous, right? Is added to potassium bromide, KBr, right? And then whatever we get from that, we're then gonna add aqueous silver nitrate to it, right? So let's write that. Let's write what happens when chlorine water is added to KBr. So the key thing to remember here, right? It's that we're looking at effectively the reactivity, right, of the halogens, right? And so let's just write out what that group looks like. So we have our fluorine at top, right? So that's F2. Then we have chlorine. Then we have bromine. And then we have iodine. So that's how the halogens are going down the group, right? So this is going down the group, right? So what we do know here is that a halogen, right, will displace anyone that's below it, the halide of the one that's below it. So in this particular case, the halogen that we're looking at is chlorine. And we want to know if chlorine is going to be able to displace this bromide ion. And in fact, it will be able to do that because chlorine, right, is above bromine in group 7. And so it's more more reactive, and so it will displace bromine from its solution that's here. It will displace those bromide ions. And so we'll end up with what we'll end up with is that we'll get KCl minus, right, plus Br. So it's displacing that bromide ion, and then that's turning into Br2 aqueous, right? And so this KCl that we see here is that solid. And then once we add the aqueous silver nitrate, then it's this KCl that's going to react with the aqueous silver nitrate. And so we're going to get, for the second step in that test, it's KCl reacting with the AgNO3. And in this particular reaction, what we're going to get is that we're going to get our white precipitate, right? So we're going to get our white precipitate of silver chloride. So we get HCl solid plus KNO3, right? So this chloride ion now comes and displaces the nitrate from here. And so that's how we end up with this AgCl solid, which is our white precipitate. So the white precipitate that's formed, we can infer that that is in fact AgCl Cl solid formed. So we can infer that from that observation. And from this first observation, what would we observe? Well, what we would observe is that bromine, this bromine gets formed, right? This halogen gets formed, and that's a reddish brown gas. So we'll see that there's a reddish brown gas formed, right? And that tells us that this bromide ion that was in the KBr was in fact displaced by this more reactive chlorine. And so because it was displaced, in effect, it was oxidized from this -1 form to the 0 form. And so that's how we got this reddish brown gas that would indicate that Br2 was formed. Okay, so that's what we would observe in this particular test. Now, in this second test, we're looking at bromine water being added to KCl followed by silver nitrate. So in this case, the reaction is this. We have our bromine water, so Br2 aqueous, and we're taking that and we're adding that to KCl, so that potassium chloride, right? And then we're going to get, well, what are we going to get? Well, so that's the interesting thing, right? So look at this reactivity series now. So now we're looking at bromine being our halogen, Br2, and bromine is going to try to displace this chloride ion, but it can't because it's below chlorine, right? Bromine is the halogen and it is below chlorine. So it's not as reactive, right, as chlorine. And so as a result, you will get no reaction in this case. And so you will just have whatever you started out with. So KCl is going to remain. So KCl remains, right? And also your bromine remains in this form where it's in this 0 oxidation state. It's just a reddish brown gas, right? Now, for the second part, you're still going to add your silver nitrate, but what you'll be adding your silver nitrate to is KCl, right? So it will just be KCl plus AgNO3, right? And that will just get you exactly what you got before, which is that silver nitrate, that silver chloride solution, sorry, which is still the precipitate of AgCl2, of AgCl plus the KNO3. Exactly what we had from up top in the second case, right? The only difference is that there is no displacement of the chlorine, whereas in this case, the chlorine displaced the bromine to form KCl, right? So that's how we had gotten KCl in the first place. It was because of this displacement, whereas in this case, there is no displacement. So we'll just have the KCl that we started out with from up here. And so we'll have KCl plus silver nitrate giving us AgCl, so that's silver chloride plus KNO3. So if we go over here, the observation that they gave us was that there's a white precipitate formed on addition of AgNO3. And again, it's AgCl that's formed when we see that white precipitate, right? So silver chloride is formed, just as we had in the first case. And then in terms of observation here, right, what would we see in this case? No reaction, right? There is no reaction. So there's nothing that's going to be observed there. So no reaction is going to see there. We're going to see nothing there. And then what we can infer from that then, right, is that these chloride ions, right, so Cl minus is not, right, it's not oxidized by the Br, because the Br2 is not as strong of an oxidizing agent as the Cl is, and so it can't displace Cl from this mixture here, right? So we see no reaction, and we can infer from that that the Cl minus is not oxidized by Br2 minus. Right, so we're left with the Cl minus in that form, and that is the form in which it reacts with the silver nitrate to give us the silver chloride that we see as the white precipitate, and of course the KNO3 is there as well. Okay, so this is how we would answer this one, and let's just scroll down a little bit here and see. Yeah, so that's for 5 marks. So this is how we would approach it. So the key thing here is to know that there are different levels of reactivity in that halogen group, right? And the ones going down the group, the reactivity decreases. And so if there's a halogen that's above another one in the series, then it will be able to displace its halide, the halide that's below it. And so that's what we saw here, is that the Cl2 was able to displace the bromide ion. And in this particular case, we saw that the bromine, which is below chlorine, was not then able to displace the chloride ion because it's not as reactive as the chlorine, okay? So that's the answer for that one. So that's part C. Let's see if there's anything else here for us to answer. So that would get us our 5 marks for part C here. All of these would get us our 5 marks. So let's clear this and go down. All right, so now